Hi, this is Winnie Penn presenting the fourth lab report of Physics 2211 about oscillations. And so for this lab, the purpose is to use tracker to analyze the mass motion attaching to a string and compare with the predicted motion model by glow script, plot the energy changes including kinetic, gravitational potential, spring potential, and total energy. These are some important physical principles in this lab. Firstly, Newton's second law, and specifically, we'll be using F net equals dp over dt. We'll also be using velocity update formula and position update formula, where Vf is equal to Vi plus F net over mass times delta t, and Rf is equal to Ri plus average velocity times delta t. And a quick preview to the results of the experiment. The observed motion of the video is very similar with the predicted motion computed from glow script. And by computing an energy change graph, we can also see how the change in total energy is equal to 0. This is the free body diagram. In this lab, we'll also be considering energy. The change in the energy of the system is equal to the work done by the surrounding and the net heat transfer Q. Some of the energy we'll be considering translational kinetic energy is equal to 1/2 mv squared. Gravitational potential energy is equal to mg times the change in height. Spring potential energy is equal to 1/2 k times the difference between stretch and relaxed length squared. In this lab, we can consider the system as mass plus earth plus the spring, so there is no work done by the surrounding, thus the change in energy of the system is 0, which also means the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy is equal to 0. This is a screenshot of the tracker page. This is where I plug in the numbers on the previous slide to the code. The period of oscillation I found through tracker is 1.519 seconds. Plug it into the equation and we can find that k is equal to 6.83. Then to find the relaxed length of the spring, plug it into the equation where the magnitude of spring force and gravitational force are equal, and I got 0.123 meters. And plugging in the numbers calculated on the last slides to here, then L is equal to the ball position minus the spring position, as this is specifically the magnitude of L minus the relaxed length of the spring. The bottom are the equations of the energy. In the loop, we first define the initial energies to be the one we have right now. Gravitational force is equal to mg pointing to the negative y direction. Spring force is equal to negative k times the difference between measured and relaxed length of the spring times the direction of it. The net force is the sum of gravitational and spring force. Then using the velocity and position update formula, we can update the boss motion. Then we also need the newly calculated position to update the spring so that the energy also changes. Since we kept the initial energies, we can then find the change in different energies during the oscillation. At the bottom right, we compare the observed data with the model data. This is a snapshot of the result. The left image shows the motion of the mass. The right graph shows the change in energy over time, and we can see how all the energy at a time period adds up to about 0. The left graph shows the x position over time. We can see how the model and experiment data match up pretty closely. On the right side, the overall shape is similar, signifying that the period of oscillation is pretty similar. The model predicts a larger max and min, so the model predicts actually more accurately for x-axis motion than y-axis motion. And then some of the key points to notice: the energy graphs all oscillate for all the energy. And then the change in gravitational and spring potential energies are opposite in signs. And then the change in kinetic energies way less in magnitude than other energies. And the model more accurately predicts the motion in the x-axis. And some possible errors are, firstly, the human error when I manually click to track the motion. And then we do not take other forces or energies into consideration, such as like drag force or like rotational kinetic energy. And then also the video was taken from an angle that might also lead to an error. And also I probably did not entirely accurately place the axis when tracking. And then for the discussion question, yes, the system I chose includes everything, so the change in total energy is 0. There's no work done by the surroundings. The orange line, delta E, remains at 0 on the graph, and other lines sum up to 0 at any certain time. And for the second question, I found the average oscillation period by finding the time to finish 3 cycles and averaging it. So we have like more accurate estimate. For X position, I have 1.6 for 2 seconds, and for Y position is 1.488 seconds. The difference can impact the calculation of the spring constant K, and indeed affects the spring force and potential energy, which may cause the deviation we see between the model and observed data.